The next operator, which is this symbol, is called bitwise ones complement. This is equivalent to negation or the not operator. Like when you say not true, it would result to false. Or when you say not false, it would return true. So the bitwise ones complement would simply reverse the value of the operand. So if the operand is true, it will become false, or if the operand is false, it will become true. The not 1 is equal to 0 and the not 0 is equal to 1 in this case. And we do this bit by bit, starting from the rightmost bit going to the leftmost bit. So if we are going to find the bitwise ones complement of the operand 46, so we say not 46, what is this equal to? Now, from the binary equivalent of the decimal number 46, we have here for 8-bit binary number, we have 00101110. And if we're going to put this bitwise ones complement there, that would become equal to, so the not 46 is equal to 1, and this is 1. This would be 0, this is 1, this would be 0, and this is 0, and that one is 0, and the last one, 0, becomes 1. So since this is the binary value of 46 base 10, the not of 46 is getting the bitwise ones complement of each bit. So as you can see here, 0 becomes 1, 0 becomes 1, 1 becomes 0, 0 becomes 1, 1 and 1 and 1 here becomes 0, 0, 0, and the 0 here becomes 1. If we're going to convert this to decimal number base 10, what would be the value? Now, in a binary number, the leftmost bit, which is this one, is called the sign bit. If the sign bit is 1, it means that this number is a negative number. If the sign bit is 0, it means that this number is a positive number. Again, the leftmost bit in the binary number is called sign bit. When this sign bit is equal to 1, like in this case, then it tells us that this number is a negative number. But if it is 0, it tells us that this number is a positive number. And since this sign bit here is 1, then this value is a negative number. The question now is, what is that negative number which is equivalent to this binary number 11010001? So let's try to solve that one by first, since this is the signed bit, then this part here, which are the bits excluding the signed bit, we call that, so the raw data now is 10100001, and we call this raw data the 2's complement of the unknown value, say we call it x. So what we are trying to find is the value of x. And what we have here, this part here, in the binary number, binary data, this part here, this is not yet the x. Instead, this is the 2's complement of x. And what we're trying to find is x, not the 2's complement. So how are you going to get the value of x given the 2's complement of x? Now, before we could answer that question, let us first do a short illustration on this binary value. Say 1, 0, 1. Say this is your x. Let x be this binary number 101, and the ones complement of x is this symbol prefixed to x, and the not of x is simply 0, 1, 0, right? Because all you have to do when you get the bitwise ones complement of a binary number is to reverse or to put the not operator on each bit. Thereby, you change the value of that bit. From 1, it becomes 0, or from 0, it becomes 1. So if this is x, 101 base 2, the not of x, or the bitwise ones complement of x, is 010, and this is base 2. We call this the ones complement of x. Okay? So getting the bitwise ones complement is by performing this operator on this operand. So we call this the ones complement of x. And for the 2's complement of x, it is simply equal to adding 1 to the 1's complement. So again, what is 2's complement of x? It is adding 1 to the 1's complement of x. So since we have this already, this value as the 1's complement, when we add 1 to it, we get the 2's complement of x. So 010 base 2 plus 1, that would result to 0 plus 1 is 1, and bring down this 1 here and this 0 here. So if we're going to convert this value, this binary value, to decimal, it would be, okay, take note of the bit position. For the rightmost, it is 1. Okay, from here, this one is 1, this is 2, and this is 4. So since the bit position for 1 and 4 are zeros, and for bit position 2, it is 1, so the decimal value of this binary number is 2, decimal 2. And when you add 1 to it, take note that this will become decimal number 3. And if we're going to convert this 2's complement 011 base 2 to decimal base 10, this is bit position 1, this is 2, and this is 4. So bit position 2 is 1, so we have this 2 plus this is 1. 2 plus 1 is 3. Okay? So it is consistent with our result here. So in summary, given a binary number like this one here, 101, to get the ones complement of that number, x, all we have to do is to apply the bitwise ones complement operator. The 101 becomes 010. Okay, we call this value the ones complement of x. And if we're going to add 1 to the ones complement, then we get the 2's complement of x. So back to our value here, the raw data 1010001, we say that this is the 2's complement of the unknown value x. So we want to know, we want to find out what this value x is given its 2's complement. So from the 2's complement, we get the 1's complement by subtracting 1 from the 2's complement. Because remember, the 2's complement of x is simply plus 1 of the 1's complement. So from the 2's complement, to get the 1's complement, all you have to do is to subtract 1 from it. So minus 1, this would become minus 1, this would become 0000101. So we call this one now the 1's complement of the unknown number x. So this is the 1's complement, 1010000. when you add 1 to it, you will get this 2's complement. So from the 2's complement, to get the 1's complement, you have to subtract 1 from the 2's complement. Now that we have the 1's complement, what is x? From this value, given the 1's complement of x, to get x, all we have to do is to apply the bitwise 1's complement, the not x, so that we will get the x. So the not of this, not of this value 10100000 is equal to, reverse each bit, this would be 0 1 0 1 1 1 1. This is the 1's complement of x, and so this is the x. So x now is equal to 0 1 0 1 1 1 1, and this is base 2 or binary form. If you convert this to decimal form, it would be equal to what? This is bit position 1, 2, 4, 8, this is 16, and this is 32. So 32 is 1, so we have 32 plus 8 is 1, plus 8, plus 4, this is 4, plus 2 plus 1, plus 2 plus 1. So what is the sum of these numbers? Is equal to 47. Okay, so the sum of this is 47. Therefore, x is equal to 47. So the decimal value of not 46 is equal to negative 47. Okay, why do we have this negative here? Because remember, from the original value we got here, the sign bit, which is the leftmost bit in the binary number, is 1. And as we have discussed earlier, 1 means a negative number. So that is why this is negative 47. Okay, let's try to run the program and check if we will get the output negative 47. So our variable here is b1, and that is set initially to 46. And our expression here is 1's complement b1, and we want to display the decimal integer value equivalent of the binary result of not b1. Okay, so what happens here is that when we run the program, this decimal number 46 will be converted to binary, and then the 1's complement operator will be performed on that binary operand, and it will then be converted to decimal value. So first, let's compile and then run the program. Okay, so as you can see here in the output, the value is negative 47. So it is consistent with our result here when we do the manual computation. So in summary, given a binary number like this one here, again, the leftmost bit value is the sign bit, and all the rest of these bits is called the 2's complement of x, where it is x that we are trying to find. So you should not be converting this value directly to decimal, because this is not the binary value of x. It is the binary value of the 2's complement of x, not for x itself. Therefore, we need to convert this 2's complement of x, which is 10100001, to 1's complement. And how do we do that? To convert the 2's complement into 1's complement of x, we're going to subtract this 2's complement by 1. And so the 1's complement now would be 101000. So again, this value here, which we got from this part here, this is the 2's complement of x. Okay, so this is the 2's complement of x, while this one here we got by subtracting 1 from the 2's complement. We call this the 1's complement of x. And to get the x itself, the x value itself, how do we get the x itself from the 1's complement? From our previous discussion, remember that the 1's complement of x is by performing the bitwise 1's complement on x. So since we are given by this, if we perform the bitwise 1's complement to the 1's complement, so it is not of x, okay, putting that operator there to this 1's complement of x, then the value we get is the x itself, right? So the not of x is simply x. So again, the not of x is simply x. So back here in our computation, given the 1's complement of x, which is this, if we perform the 1's complement operator on this 1's complement value, then we get the value of x itself. So the not of these bits would be 0, 1, 0, 1, 1, 1, 1. So this is now the binary value of x. Okay, that's base 2. This is value of x. And what is the decimal equivalent of this binary value of x? Okay, so this is starting from the rightmost bit. This is bit position value 1. This is 2. This is 4. This is 8. This is 16. This is 32. And so on. So we are interested only of those bit positions having a value of bit 1. So this is 32, this is 8, and this is 4, this is 2, and this is 1. So you add all of those integer values having a bit value equal to 1. So that is now 32 plus 8 plus 4 plus 2 plus 1. So that is equal to 47. Okay? So this binary value, which is the value of x itself, is equal to, in decimal form, that is decimal number 47. And therefore, going back to the value that we are trying to find, which is the not 46, which is the bitwise 1's complement of 46, this is equal to, as mentioned a while ago, the sign bit is 1, which means that it is a negative number. Therefore, this is negative 47. So that is the value of not 46, or applying the bitwise 1's complement on the value 46. So again, the bitwise 1's complement of 46 is equal to negative 47. It is negative because the sign bit here is 1. And this value here is the 2's complement of 47. So we are done with this operator, the bitwise and also the bitwise inclusive OR. This is the bitwise exclusive OR, the bitwise 1's complement. And this time, let's discuss the bitwise left shift and the bitwise right shift. So this operator here is called bitwise left shift, and this one is bitwise right shift. So say we're going to say, if we let this to be B1, B1 is equal to binary number 001011110, which is equivalent to decimal number 46. So say B1 is decimal number 46 or equal to this base 2 or binary number. So what is the value of B1 left shift ones? 1 here, this 1 here is the number of times you shift the bits going left. So if B1 is this binary number, shifting all the bits 1 bit position going to the left, it means like you are moving all of this, you are dragging all of these bits 1 position to the left. So this will now become, so this one moves there, out there, so it will be positioned in the bit 9 position, and this one here would move there, this one would move here, so each one will move 1 position to the left. That's the effect of bitwise left shift. So B1 left shift 1 is equal to, so this one moves there, so this becomes 0, and this one moves there, so this is now 1, and this one moves at this position, so this becomes 0, this one moves here, so this becomes 1, and this one moves here, this becomes 1, this one moves here, this becomes 1, and this one here, the last bit position or the rightmost bit position moves here, so this becomes 0. So take note that this one will be out of this 8-bit position, so the 0 here is lost. If this is 1, this would be a significant data loss. But since this is 0, it has no effect to the value of this variable B1, since that is 0. Again, since this is 0, if this is lost, since you shift this out to the left, this will not have any significant effect on the value of B1. It will not result to data loss because it is 0. But if it is 1, that would be a significant loss. So we consider that data loss when this is 1. So shifting 1 bit position to the left would result to this value. And we have here a vacant position, which is this one here. The vacant position will just be set to 0. So this is the binary value of this expression B1 bitwise left shift 1. So the value here is the number of steps you shift the operand B1 to the left. If this is B1 left shift twice, so the 2 here is the number of bit positions to move. So if that is 2 now, it would be that this value here, the one here at position 32, will move 2 positions to the left, first and then second. So the one here will be positioned at 128, and then this will be positioned next to this. So this one goes here, and this one goes here. And so the rest of the bits, 110, will be here also, 110. And as a result, there will be 2 vacant bit positions on the right side, since the previous occupants of these vacant positions are 0 and 1 respectively, and you move these 2 positions to the left. So the 0 originally here will move 1, 2 positions. So this is now where you place bit 0, which is originally at bit 1. So now it is at bit 4, or this this bit position with integer value 4. So converting this to decimal value, first B1 shift left 1, this is now equal to, this is bit position integer value 1, 2, 4, 8, 16, 32, 64, and 1 to 8. This is now 64 plus 16 plus 8 plus 4 in the binary value. So this is 64, 16, 8, 4, and okay, this is 0, so this is plus 0. So what is that now? What is the sum of the products? We have 64 plus 16 plus 8 plus 4. So the answer is 92. So B1 shift left 1 is equal to 92. Base 10. This is decimal number, which is equal to binary 010, this one here, 010111100. That's base 2. So this binary number, which is your B1 shift left 1, is equivalent to decimal number 92. How about the B1 shift left twice? What is the decimal value of this binary number? So take note, these two vacant spaces here are set to 0. So this bit position is integer value 1 to 8. So you have 1 to 8 plus, this is 1 also, so plus 32. This is 16 plus 16. This is 8 plus 8. And that's also, what is 1 to 8 plus 32 plus 16 plus 8? It is equal to 184. This is equal to 184. This 184 is base 10, or this is a decimal number, and the equivalent binary of this decimal number is this one here. That's the base 2, which is the B1 shift left twice. So in summary, this is B1 shift left twice is equal to 184 base 10 decimal number, which is equivalent to 1011100 base 2. Okay, let's go back to our program and try to run this one. So printf, the second printf here is B1 shift to the left. The first is 1. This second is shift to the left 2. So compile and then run the program. Okay, let's put a new line here so that each value will occupy one line. Compile, run. Okay, now look at the output for the first printf, and that is to display the decimal value of the expression B1 shift left 1. It's 92. Okay, that's consistent with what we got here in our manual computation. And for the shift left twice or 2-bit position, the decimal value is 184. Let's check our output. Okay, it's 184. Okay, so look at the source code. For the first printf, the output is 92, this one. And for the second expression, it is 184. So this is for B1 shift left once, and this is for B1 left shift twice. Okay, so that is the same as what we have here, 92 for the first output. For the second output, it's 184. Now, what have you noticed with the operation to perform bitwise left shift When you do it for one shift or two shifts, take note that every left shift, every bitwise left shift is equivalent to multiplying the operand B1 by 2. So again, every bitwise left shift is equivalent to multiplying the operand by 2. So one shift like this results to the decimal number 92. The original value of B1 is 46. So from this, that bitwise left shift is equivalent to multiplying by 2. When we multiply 46 by 2, take note the result is 92. So again, one bitwise left shift, like this one, is equal to multiplying the operand B1 by 2. So as you can see, the result is 92. If we shift B1 two positions to the left, then you are like multiplying B1 by 2 twice. So 46 times 2, that's the result of the first or the one left shift, which is 92, right? And then since we are shifting it twice, you multiply it again by 2. So this is the first left shift. This times 2, here is the second left shift. The first times 2 is for the first left shift. The second times 2 is for the second left shift. So 92 times 2 now is equal to 184. 2 times 2 is 4. 9 times 2 is 18. So the result is 184, which is the same as the value we got here when we run our program and when we do the manual computation, 184. Okay? So again, take note, every time you perform bitwise left shift, you are like multiplying the operand B1 by 2. So when you left shift twice, you multiply the operand B1 by 2 twice also. So the B1 shift left 1 here is equal to 46 times 2, which gives you 92. The left shift twice gives you 184, which is equal to 46 times 2 times 2. And lastly, for bitwise right shift for this operator, so if we're going to get B2 right shift once and B2 right shift twice, okay, let's find out what these two expressions are equal to. So B2, this is our B2, which is equal to 108, a decimal number, and the equivalent binary number of 108 decimal number is this one here. So when we perform bitwise right shift once, we're going to move this one to the right, one bit position to the right, and this goes to the right, this one goes to the right, this one goes to the right, this one goes here, and this one moves there, this one moves there, and lastly this one. So this would create a vacant bit position here. So the result would now be a vacant bit position here because this one moves there. So this one is 0. This one moves here. So this is 1. And this one moves here. So this is 1. And this one moves here. So this is 0. This one moves there. This is 1. And this moves here. So this becomes 1. And this one moves there, this becomes 0, and the 0 here moves out. So if this is 1 here, moving this out would cause data loss. But since this is 0, it has no value, and so the effect of moving this out is insignificant. So the vacant position here would be set to 0, just like what we did when we shift to the left earlier. So B2 right shift once is equal now to 0, 0, 1, 1, 0, 1, 1, 0. Okay, that is base 2, the binary. And if we are going to convert that to decimal, this is equal to, the bit position value of this one is 1. This is 2, 4, 8, 16, 32. So you add all those values having bit 1. So this is 32 plus 16 plus 4, 8 is not included, plus 2, and 1 is not included. So that is now equal to 54 base 10. And shifting it to the right twice, okay, for the second expression, shifting it to the right twice, it will now be shifting it to the right twice. This one moves 1, 2 to the right, 2 positions to the right. This one would move 1, 2. So 2 bits are lost. Okay, so because this one moves 1 first step and 2, because you are going to shift twice. So these two are gone out of the binary value, and this one here would move 1, 2, so this becomes 1, and this one moves 1, 2, this becomes the second, and this one moves 1, 2, this becomes the third going left, so this is 0, and this one moves twice to the right, 1, 2, so this becomes the 1, 2, 3, 4. The fourth position from the right is equal to 1, and this one here moves 1, 2 at position 16. Okay, so this is 1, and this is 0, so this is 0, and since you have here 2 vacant bit positions now, these 2 vacant bit positions will be set to 0. Okay, so the binary value now is 0, 0, 0, 1, 1, 0, 1, 1. That's base 2. So if we convert that to decimal value, it will be what? This is bit position 1, 2, 4, 8, 16. Okay? So get the sum of this. 16 plus 8. 4 is not included because this is 0. And plus 2 plus 1. 16 plus 8 plus 2 plus 1. That is equal to decimal number 27. That's base 10. Okay? So what have you noticed with the values for these two expressions? Notice that B2 is 108. B2 is equal to 108. When you perform right shift once and the result is 54, take note that you are like dividing the operand B2 by 2. Okay, so take note that every bitwise right shift is equivalent to dividing the operand B2 by 2. So 1 bitwise right shift is equal to dividing the operand by 2. This is only one right shift, so only once you divide the operand B2 by 2. So what is 108 divided by 2? 108 divided by 2 is equal to 54. Okay, so once again, every time you perform bitwise right shift, that is equal to dividing the operand by 2. So from 108, the operand is equal to 108, divided by 2, the resulting value is 54. And since we perform bitwise right shift twice here, it is equal to dividing the operand B2, which is 108, by 2 times. The first divide by 2 is for the first right shift. And take note, this is equal to 54. The second time you divide it by 2, that's for the second right shift. 54 divided by 2 is equal to what? 27. Okay, so that's why, as you can see here, the value is 27 because we perform bitwise right shift twice, and every right shift is equivalent to dividing the operand by 2. So you divide 108 by 2 twice, resulting to 27. Okay, so let's try to run the program now. Okay, so our operand is B2 this time. And we perform right shift once and right shift twice. So compile it and run. Okay, so that's our output for the first printf, and that is to output the decimal value of this expression B2 right shift once. The answer or the output is 54. Okay, it's consistent with the result we have in here, 54. And for the second expression, it's B2 right shift twice. The output is 27. Okay, and that is consistent with our result in here, 27.